Alright, let's determine all extrema, intervals of increase and decrease, points of inflection, and intervals of concavity for the following function. The k of x is equal to 1 half x to the power 4 minus 2x cubed. So let's start with our extrema. So we need to do the first derivative test. So we're going to be using derivative testing to glean all of this information from our function, right? So this is our first derivative test. And using my first derivative test, k prime of x here is basically 4 over 2x cubed minus 6x squared. Okay, so still using our first derivative test. Sorry about that. Okay, so we get 4 over 2x cubed minus 6x squared. So k prime of x you can write as 2x cubed minus 6x squared. Okay, and if you wanted to solve for your critical points, well, we're going to let k prime of x equals 0 because we know that the derivative at maximum and minimum points are going to be 0. The slope of the tangent is going to be 0, right? So we can understand here that 2x cubed minus 6x squared is equal to 0. So I'm going to factor out 2x squared here, and that's going to give you x minus 3 is equal to 0. So using this, you can figure out that your two critical points, or your critical numbers of x, are x is equal to 0 and 3. Right, so after you figure out those points, what you want to do is you want to find the y equivalent of those points. So the points will be 0 and k of 0 and 3 and k of 3. Okay, so in that case, k of 0 here is basically equal to 0, so you have the points 0 and 0. And k of 3 here is equal to 1 half times 3 to the power 4 minus 2 times 3 cubed. So k of 3 is going to give us 1 half times 81 minus 2 times 9, which is 81 over 2 minus 18, right? So k of 3, if you wanted to write it as a decimal, you could, right? Or we could basically write it as 45 over 2. Okay, so the other point is going to be 3 and 45 over 2. Okay, so your extrema, maximum or minimum point, one of the extremas occur at 0 and 0, the other extrema occurs at 3 and 45 over 2. Okay, we just don't know how to distinguish between which one's the maximum, which one's the minimum without actually sketching this, but we can test this, we can determine this by using the second derivative test. We also want to figure out intervals of increase and decrease of the function. So let's look at intervals of increase and decrease. Okay, so interval of increase, interval of decrease, right? And we have to still be using our first derivative, right? So you can notice here that I simplify the first derivative in this scenario. So this is basically k prime of x is equal to 2x squared times x minus 3. Okay, so this is our first derivative. And you can notice that if you wanted to figure out the intervals of increase, the interval of increase occurs when the first derivative is basically greater than 0. Well, we can understand that the 2x squared here will always be positive. The only thing that will be different is the x minus 3, right? So we need to figure out what intervals occur. When is x minus 3 going to be greater than 0, right? So in this case, x would be, when x is greater than 3, we're going to have a positive value, right? So we have an interval of increase when x is greater than 3, or you can write x belongs to 3 and positive infinity. Right, we'll also have an interval of decrease in the opposite scenario between negative infinity and 3. Okay, so those are the intervals of increase and decrease. Now let's shift gears, and this time we're going to be looking at points of concavity. All right, so if we're looking at points of concavity or intervals of concavity, we first need to figure out our point of inflection. So let's do our second derivative test. Okay, so let's look at our second derivative test here. And for me to do my second derivative test, I need to first find the second derivative. So I'm going to find k double prime of x, which is the derivative of k prime of x. So I'm going to do derivative with respect to x of k prime of x. So you have 2x cubed minus 6x squared, and you basically get k double prime of x is equal to 6x squared minus 12x. Okay, so that's your second derivative function. To find your point of inflection, I'm going to let my second derivative function k double prime of x equals 0. So you get 6x squared minus 12x is equal to 0. I'm going to factor out 6x. You basically get x minus 2 is equal to 0. So therefore, a point of inflection occurs at x is equal to 0 as well as 2. Okay. Now these are specifically just the x values of the point of inflection. If you want to find the y values, well, let's take our original function. I'm just going to write this out here. Okay, so this is our original function. K of x is equal to 1/2 x to the power 4 minus 2x cubed. Okay, so we take our original function and we can plug it in, right? So this point here, the 0 and 0 point, right? So one of your point of inflections occurs at 0 and k of 0, which we already kind of determined as 0 and 0. The other point of inflection occurs at 2 and k of 2, which is basically 2 and k of 2 in this case. I'm just going to do it out here. K of 2 in this case is 1/2 2 to the power 4 minus 2 times 2 cubed, which is 2 to the power 4, 16. 16 over 2 is 8. 8 minus 8 times 2, which is 16, which is negative 8. Okay, so k of 2 here is negative 8. Okay, so these are our 2 points of inflection, right? So our 2 points of inflection are 0 and 0 and 2 and negative 8. Okay, so those are our points of inflection. Okay, POI. So now we have our point of inflection. What we want to do is we want to also determine our intervals of concavity. So if we're looking at intervals of concavity, we're still going to be using our second derivative. Right, so this is our second derivative. Right, and you want to kind of look at this in its factored form. So k double prime of x is equal to 6x x minus 2. Okay, so I'm going to be looking at the second derivative function in its factored form. K double prime of x is equal to 6x times x minus 2. And the way we look at intervals of concavity, recall that if the second derivative function is greater than 0, the graph itself would be concave up. If the second derivative function is less than 0, then the graph itself would be concave down. So let's take a look at designing a number line to map out our intervals. So if we're looking at mapping out our intervals here, our point of inflections we stated were 0 and 0 and 2 and negative 8. So I'm just going to plot the x values of the points of inflection. Right, this is positive infinity, this is negative infinity, right? And we can understand that between the interval of negative infinity and 0, if I plug in a value, let's say that between the value interval of negative infinity and 0, let's say that x is equal to negative 2. So I'm going to do f double prime of negative 2. And if I do f double prime of negative 2, right, you're going to see that you're going to get 6 times negative 2, which is a negative, and then negative 2 minus 2 is basically negative 4 to 2 negatives, so you basically have a positive, right? So if you have a positive, then this portion here is concave up. So this is a concave up portion, right? Then we look at the interval between 0 and 2. So the intervals occur between the critical points. In this case, they are the point of inflections, right? So between 0 and 2, let's say x is equal to 1. So we do f double prime of 1. If we do f double prime of 1, that's going to give us positive, negative, and then this would be negative, right? So if the overall sign of your second derivative is negative, then we basically get a concave down portion. And the last interval here is between 2 and positive infinity. So if we're looking at 2 and positive infinity, going to pick a value between that interval. Let's say x is equal to 3, right? Should have done that in green, but it's okay. X is equal to 3, so you're doing f double prime of 3. If you do f double prime of 3, you're going to get positive and positive, so the overall sign is positive, and if the second derivative function is positive, it's a concave up portion, right? So we can notice here that for intervals of concavity, it's concave up when we're looking at negative infinity, when x belongs to negative infinity and 0, union 2 and positive infinity. Okay, so both of those intervals will create a concave up portion, and we also, for concave down portions, x can belong to 0 and 2. Okay, so you can notice that we can get tons of information by using these derivative testing, right? Whether it's critical points like the extrema, the interval of increase and decrease, right? Points of inflection or intervals of concavity. And together you can piece this together eventually to create a sketch of your function, a very well-defined sketch. And really that's the purpose of calculus, right? It's optimal for curve sketching.